Sir, can I able to see the screen now?
Yes, sir.
Yes, sir, it's visible.
Okay. So today we are going to see about filter design. Okay. So what I'm going to do means,
Sir, can you make it in presentation mode? Yeah.
yeah, I have shared as a presentation format. So actually, before starting in HFSS design, so I will give some introduction about the filters. Okay. So there's an overview. Okay. So filters is just a frequency selective device. Okay. So mainly for used in a lot of RF applications. Uh, so it can be different types like low pass, high pass, and then band pass, and band stop. So mainly for low frequencies, we can go for low pass filtering the certain frequencies. So and for high pass filter, we can filter the high frequencies. So similarly for band stop and band pass, we can allow certain frequency bands, and we can stop the certain frequency bands in band stop filters. So used in a lot of applications, mainly in wireless. Filters is actually used for better performance in achieving the results. Okay. So normally the fabrication of this one is filters is very easy and compared to different RF and microwave components. So so there are different types of each filters are there, like ladder type filters, or you can go for step impedance filter types. And here you can see this is a step impedance format. Okay, so input and output, and in between you can extend this structure. Okay, so you can use a certain LC components, and we can do. So in HFSS, we can able to create microstrip based filters. Okay, so we cannot create a direct circuit components, and we cannot do a filter design in HFSS. So that option is not available. So in HFSS, we can able to do microstrip based filter design. So in order to do that kind of designs, normally we have to find the dimensions. Okay, so we can go for different types. So under today we are going to see about the bandpass filter design. So we can able to create a bandpass filter design in different formats. Okay, so one of the form is actually the n-coupled, and then you can see this is n-coupled. So H to H, you can see the coupling will be happen between the in the filters. Okay, similarly parallelly coupled filter designs will be there. So here you can see parallelly will create the microstrip based designs in order to get the filter results. Okay, so these are all microstrip based filters. Okay, so similarly, so today we are going to design this parallel coupled filter in HFSS. Okay, so we will see about hairline structures, interdigital line, and short circuit stub-band filters. Okay, so this is a hairpin line structure designs. So here you can see, so this is a port, this is another port, so 1 and 2 ports, and between you can see a lot of microstrip designs can be happen. So you can see the shape is actually almost like hairpin lines, so it will be like inverted shapes. Okay, the inverted U shapes. So in between there will be gaps will be there. So normally the coupling of feeds will be happen between these hairpin line structures. And similarly, you can also create the filter design, bandpass filter design. So here you can see interdigital line filter. So you can see it is almost same like the hairpin line structure, but it will be a direct rectangular shape filters. Okay, it will be almost kept parallel in between these, but the distance between these filters and the fixed structures will also decide the results. So in order to design an HFSS, normally you have to find out the width and then length and then the spacing between the resonators, each resonators. So that will give the better results. Okay, so in order to achieve a better results in filters, need to optimize the width and length and then the gap between these So that is the spacing. So you can also able to create this kind of stub based acoustic filters. You can see you can create a parallel like this structure when compared to a main acoustic line. You can parallelly create, so you can able to achieve a wider bandwidth if you are using this kind of steps. Okay. So coming to bandpass filter design using HFSS. So today we are going to design for 2.4 gigahertz. Okay, so that is with a third order filter. So that will achieve a bandwidth of 10 percentage with equal ripple in pass band. That is a 0.5 dB. So for this microstrip based filter design, I'm going to use the FR4 substrate. So on top of that, we are going to design the filter. So they'll have epsilon r value as 4.4. Okay, so the thickness, that is the height of the substrate is 1.6 mm. And we are going to see about the S parameters and then the field results. So for example, I have taken this filter design as a tabulation from the David and Pozar book. Okay, so this is a Chebyshev filter. So for the order 3, we can take the tabulation values. So this is a values. Okay. So various type of filters can be designed with the parallel coupled transmission line. So this is actually a coupled line transmission line. Okay. So we are going to design this kind of filter today. So here the tablet is mainly for Chebyshev filter. So here you can use the n number of low pass filter prototypes to connect it and make it as a band pass filter. Okay. So for the order 3, we are getting the values, these 4 values. So we are just taking these 4 values from the tabulation and we are going to start calculation of the dimensions. So first we will calculate the admittance. So based on the admittance, we will find out the impedance. Okay. So these are all the characteristics admittance values. So we are going to use a formula. So this is a formula. Okay. So Jn comma n plus 1 divided by y naught, it is equal to square root of I by 2. So this is actually f by w is the fractional bandwidth of a filter. Okay, divided by gn plus 1. So for filter for order 3, we are going to take the value 0, 1, 2, 3 as z. Okay, so j is equal to 0, 1, 2, 3. We are going to substitute in this equation. Okay, and we are going to calculate the values. So these are all the calculated values when substituting the values 0, 1, 2, 3. Okay, using the theoretical formula. So once we find the values, we can able to find out the characteristics admittance. This is the characteristics admittance values. From this, we are going to find out the impedance values. Okay, so for finding the impedance values, we are going to use a formula, this one. So the impedance, there are 2 types. Okay, so one is actually the even mode impedance and odd mode impedance value. Okay, so why we are going for the impedance admittance calculations are in order to find out the dimensions of the filter. Okay, so ZO is the even mode, ZO is the odd mode impedance formula. Okay, so we are just substituting the values in these formula for 0, 1, 2, 3, and we are just calculating. This is an example for z is equal to 0. Example is that we are finding the even mode impedance and odd mode impedance value. So this is for z is equal to 0, even mode and odd mode. Similarly for 1, 2, 3, these are the values calculated. So using these 2 formulas. Okay. So there are certain online calculators are there for finding the acoustic line filter. Okay, so that is for finding the dimensions of the acoustic filter. So I'm leaving the link here. Actually, this is a website called soundforge.net. Okay, wcalc.soundforge.net. So under the /cg hyphen bin slash couple underscore microstrip.cga. Okay, so this link will take you to the online calculator. So there are different websites are there. So in the Google you can search for microstrip line calculator. Okay, so it will show you a lot of websites, and here you can also go to this link. Okay, so once you find the even mode and odd mode impedance values, so we can go to this website. So I'm clicking on the link, so it will take outside the my Google Meet, and it will take you to the browser. So in this you can able to find out the width, that is the filter width, that is that each resonator width will be there. So this is the width. So we need to find out the width, and then S is the spacing between these resonators, and L is the trace length, the length of the each resonator. So we need to calculate the first three. Okay, so for that we need to set the metal thickness. Okay, and then metal thickness is how much the width, that is the thickness of this each resonators, that is the traces. Okay, so similarly here to enter all the properties of the particular substrate and resonators. So substrate thickness, the substrate dielectric constant, and then loss tangent of the substrate. So everything we need to enter the values. So from this to this we need to enter the value, and also the frequency. Okay, so once you have entered the frequency means, so all these values means, so just click analyze. So automatically, so here these even mode and odd mode impedance values will be calculated. So for that you need to choose even mode and odd mode. Okay, so you need to choose this even mode, odd mode, and then analyze. So these even mode and odd mode impedance values also to be calculated. Either you can use this directly this calculator to find even mode, odd mode impedance, or you can refer the theoretical formula from the presentation. Okay, so from that, after that, if you find these even mode, odd mode impedance values, so go to this calculations. So set the units and which unit you want to calculate. So you can choose a millimeter or a centimeter, whichever unit you want, and then click on calc. So automatically the dimensions, spacing, within length will be calculated. Okay, so according to the frequency and substrate properties, and then the even mode or more impedance values. Okay, so for each resonator's width and length and spacing, you can find out using this calculator. So this is a one method. If you want to find out the width and space and length using the theoretical formula, so we can use this formula. So this is the formula here. Okay, so W by H, this is the formula for finding the width of the each resonators. S is nothing but the formula for finding out the spacing between the resonators. Okay, so spacing, width we have to calculate initially. After calculating the spacing and width, we have to calculate the length of each resonators. So for finding the length, so this is the formula here, you can see. So these are all theoretical formulas. Okay, so you can just take this equation, length equation, or you can substitute that values. Okay, now we can enter the values here. So these are all the calculated values for each resonators, 1, 2, 3, 4. Okay, and here you can see the spacing between there, and then length and thickness. Okay, so anyway we are going to create the first one here, and then we'll create the second one, and we will duplicate this again, and this is the last one. And then once you created this one, we will create actually two, and then we will connect and we'll duplicate again here. Okay, so this kind of parallel coupled filters we can easily create using the duplication method in HFSS. So actually The spacing between the resonators we have taken from as per the theoretical calculations, we have got values as 0.046 spacing values. So now to get a better matching, okay, so we are just taking the optimization value to 0.1 mm. Okay, so that already have optimized. So based on that value, I'm telling. So coming to that design part in HFSS. So I am just opening the software. So there is the ANSYS electronic desktop. So anyway, all the dimensions are calculated for the millimeter units. Okay. So in HFSS, the default unit option is millimeter. So no need to change the unit option. So I'm going to start from the setup. Okay. So I'm going to insert a design. So once you open the HFSS, you can see in the top, the project option is there. So I'm going to insert a design under the project one. So go to insert HFSS design. Okay. So once I inserted the design, so you can able to see this workspace window like this with Cartesian coordinate system. Now, so I'm going to start the layer by layer design. So I'm going to use an option called terminal in the solution. So normally, if you are going for a multi-layer design in HFSS, we can go for terminal option. So go to HFSS solution type. Okay. So this is an option called terminal, and then we can go click OK. So now I'm going to start the design from the substrate creation. Okay. So size of the substrate is actually 30 cross 100 cross 1.6. Okay, there is a width is 30, length is 100 mm, and size is there is a thickness. The height is 1.6 mm. I'm going to use FR4 epochs. Okay. So go to draw. For creating a substrate, I'm going to use an option called box. So go to draw box. So once you are in draw mode, so here you have to draw the box. So click once anywhere and move your mouse and make it like a rectangle. So click once. So just move your mouse above or below to make it like a box. Click once. Okay, so in HFSS, whatever we are selecting, it will be highlighted in pink color defaultly. So just click outside. Now you can able to see the default box is created with green color. So randomly have clicked and we have created the box. So now we have to change the positions and dimensions. Okay, according to our calculated dimensions. Okay, so here this is a solids. You can see under the solids in the 3D modeler window. You can see under vacuum now our box one is there. So double click on the box one. So first of all, we will rename this one as substrate, and the material. Go to edit. So default material for the 3D objects will be vacuum. So you have to give the our own material according to your design. So FR4 epochs have changed automatically highlighted. So this is your substrate material, and similarly you have to set the color. So I'm choosing a different color. So give some transparency between 0 to 1. So any value you can give. So I'm giving a value as 0.7. Then click OK. So click outside the substrate. Now you can able to see that change in the properties, name, material, and then everything gets changed, the color also changed. So because of substrate, double click on create box, and I'm going to start from the dimensions first. So axis I'm going to take it as minus. So why I'm having minus 30 means, say in HFSS we can start our design from any particular coordinate system. Okay. So if you are going to start from different coordinates, or positive and negative symbol for each dimensions also will change. That is negative or positive. So if you are starting from the positive side, if you are going towards the negative side, you can take the positive and negative symbol. So here, so this is 15, 5t, 0. Okay, so 15, 50, 0. So that is nothing but the x size minus x size divided by 2 is x position. Minus x size is minus of minus plus 30 by 2 is 15, 50 is, so minus of minus 100 divided by 2, this is a y position, so z position I'm going to start from the 0, that is the origin. Okay, so you can start from any particular position, just I'm taking the equal half of the dimensions from the negative and positive coordinate system. So here you can see it is from negative coordinate system, and half of this will be in the positive coordinate system. That's why I'm taking the negative symbol, so in order to achieve the values. So here 15, 50, 0. Now click OK. So now the dimensions on pushing gets changed. So press Ctrl D in your keyboard, and you can able to see the entire design. Okay, you can use the rotate option at the top, and you can rotate and see the design. Now, so I'm going to create a ground plane for this design. Actually, I'm going to create a ground plane using an option called draw box. So actually, this ground plane has some thickness. Okay, so here, for easier creation of ground plane, I'm going to tell you one method. So you can create a ground plane by choosing the bottom corner. So this is a corner. You can choose any corner of the substrate. Okay, so here you can see this is the top corner. If you place the cursor, and this is the bottom corner. If you want to make it clear, you can still use the option called zoom in, and you can choose any of the corner. I'm choosing this corner. Here, this is the top corner. If you place the cursor, black box will show. So go to the bottom corner. So where it will show black box again. Exactly on the corner, if you place the cursor, it will show. So click once on the bottom corner, and press Ctrl D in your keyboard to come out of zoom. Okay, so now go to the diagonal, opposite diagonal. So exactly in the corner, if you want to still make it zoom in that corner, you can use the zoom in option. So you can still zoom, and you can, okay, so I'm zoomed in. Now go to this bottom corner. So where I have clicked that corner, you have to go diagonally, and then in the diagonal corner you have to click exactly where you'll get the black box. So click once. Now press Ctrl D. Now here in the box, under the sheets, actually it is box. Okay, so here we have not given thickness. That's why it is showing under sheets as a box. Okay, so what I'm going to do means I'm going to give some thickness as 0.02. So it should be this ground plane should be below this substrate, that is the bottom of the. So I'm giving minus 0.02. Okay, so this is going towards the negative direction. Okay, so if you give positive symbol, it will move towards the positive z direction. So that means the thickness of that ground plane, it will overlap with the substrate. Okay, so that's why I'm giving negative symbol. So it will go below my minus z direction. Now click OK. So now we will create the resonator geometry. So first we will create the center resonator. And okay, so this is a pusher and dimensions. So for that I'm going to use the drawing option as draw box. So I will draw a box. So it will have some thickness. The thickness as 0.02. So I have to start the design at the top of the substrate at 1.6 is on the top. So we're going to draw box. So draw a box anywhere, and later will change the positions. So I'm drawing a box. So this box one is actually the ground plane. So you have to change the name as box one for ground. Actually, I have not changed. So name as ground. I click on the vacuum and go to edit and set the material as copper. Okay, so copper, and then click OK. Similarly, you can give a different color. So I'm giving a red color. Give some transparency. So now we have created actually the new box, that is this box. So this is going to be the center resonator. So double click on this one, this box 2, and rename this as resonator. And this is resonator 1. And click on the vacuum and choose the material as, this is a conductor. I'm giving material as copper. And similarly give some transparency. So bottom and top layer material as red color I'm giving. So here under the resonator one, now double click on create box. So we need to change the position and dimensions. So position is minus 1.765, comma minus 16.76, comma 1.6. Minus 1.765, comma minus 16.76, comma 0.6. So this is excess is 3.53, and then y size is 33.52. 33.52, and z size is 0.02. So this will be on the top. So we're giving plus 0.0 to be having thickness. It will move towards the positive z size. So click apply, and then OK. So not to identify easily, just click on the resonator and give some different color. Yes. So now we are going to create the resonator at this side. There is another resonator. Okay, so we are going to create two resonators. Okay, so after that we'll unite that one. Okay, so for that I'm going to draw box. So go to draw box. So draw a box. Draw box. So draw a box anywhere. Now we'll change the position and dimensions. So under the vacuum now, so double click on the box one and rename this as resonator 2. The vacuum change to copper is the material. Set the different colors. I'm going to keep all the top resonators. That is the color as yellow. So resonator 2, under the resonator 2 now, here in the model window, so under the resonator 2, double click on create box. So I'm going to change the position and dimensions for this second resonator. So that is minus 2.196 comma 0.264 minus 2.196 comma 0.264 0.264 comma 1.6. So all the resonators will be on the top of the so X size and Y size. So X size is minus 3.53 and then Y size is 16.76. So minus 3.53. Z size is 0.03. So sorry, this one X size is minus 3.53 and Y size is minus 16.76. Okay. So here apply. So actually the Y size is plus 15 points at 16.76. Okay. So as you can see now here, there is a gap between the center resonator and then this resonator 1. So there is a gap. So here we are going to create another box. Okay, so we will draw a box and draw a box. So this box created under vacuum, you can see there is box 1. So below the newly created box 1, so double click on create box. So the question is minus 5.726 comma 17.02. Seventeen point 0.02 comma 1.6. So Z size is 0.02. Okay, then apply. So X size is 2.54 And y size is the length, that is 16.98. So 2.54 and 16.98. So now click OK. So we are just going to unite this resonator 2 and this newly created box 1. Okay. So select the resonator 2 and then select the box 1. So use the control button on the keyboard and select these two. And then in the top you can see unite option is there. So click on the unite. And then you can see the edge portion gets united and it is a single object. So now you can see under the solids, now the entire thing is actually the resonator 2. So if you click on the resonator 2, now the entire object will be selected. So you can expand the resonator 2 and you can see it is united with box 1. So actually the box 1 is united to resonator 2. Okay. So you have to create another couple line in this opposite side of this. So I have to create the resonator this side. So how to do means you can use this duplication method. So we'll select the resonator 2. So you can see around axis. If you place the cursor over that, it will show duplicate around axis option. Okay. So duplicate around axis option, if you click means in the top left it will ask in which axis you want to duplicate. So actually you have designing in X and Y plane, that is horizontal plane, and Z axis facing towards the top. So if you are choosing around the Z, so actually we will design in the same plane. So around the Z axis. So Z is facing towards the top. So around Z means it will be created in same plane. So actually you have to create it in same plane only. So, okay. So the angle, how much you want to rotate and you have to duplicate. So class. I'm just giving a perpendicularly, sorry, it is a 180-degree angle I'm going to give. So it will be created in the opposite side and it will be parallel to all the, okay. So total number I'm giving 2, that means including the source one. This is the first one and this is the duplicated one. So here you can see the dotted black lines, it will show where the structure is going to be created exactly. Now click OK and you can see this is a newly created one and this is actually the resonator 2 underscore 1. So double click on the resonator 2 underscore 1 and rename this as the resonator 3. Okay. So here below the resonator 2, you can see duplicate around line is there. So you can double click on duplicate around line and you can change the angle and then total number whenever you want. Okay. So now we have to create another resonator this side and we have to duplicate this side. So the another resonator will touch this side and then another resonator will touch this side. So 1, 2, 3, 4, this is the center resonator. Okay. So go to draw box again. So draw a box. So under this vacuum, you can see box 2 is there. So double click on this box 2 and rename this as resonator P and choose the material as copper and then set the color and transparency. So you can give the same color or all the top resonators. And then transparency you can set between 0 to 1, any value you can do. Same like 0.7 I'm giving, then apply. Now another resonator 3, double click on create box. So here the position is minus 5.86826 comma 17.284 comma 1.6. So enter the position. So they did the default random positions. So minus 5.826 comma 17.284 17.284 1.6 like the top layer. X size is the width, and then Y size is the length, and Z size is the thickness. So I'm giving minus 2.54 as X size and 16.98. So minus 2.54, 16.98, and Z size is 0.0. Now click OK. So now you can rotate to the opposite side and you can able to see the resonator. Actually, there is a gap. I think it is not clearly visible. Gap. You can still zoom in, and you can see there is a gap. It will be around a 0.1 mm gap, I think. So you are going to create another resonator that will touch this end. Okay. So if it is touching this end, the end of the substrate, you can give the input at this side. On the opposite side, this is this end. We are again going to duplicate the same resonator this side. It will touch here. This will be the port 2. Okay. So this is a 2-port device. So go to draw. Again box. And draw a box. So under the unassigned, you can see box 2 is there. So under the box 2, double click on create box. So Z size is always 0.02 for this design because standard thickness I'm going to take it as 0.02. And the position is minus 5.826 comma 34.264. Minus 5.236. So X size is minus 3.12. That is the width of this one. And then Y size is 15.736. So X size is minus 3.12. Then the Y size is 15.736. 15.736. And then apply. So Z size is 0.02. And then so here this box 2 is created, and you can see this is exactly created, and this is touching the end of the substrate. You can still zoom in. Okay, so this is touching. So select this resonator 3 and this newly created box, and then here you can see unite operations in the top. So click on the unite. So So now the edge portion gets united. This is 5.826. So here you can see this side the shape gets changed. Okay. So even if you are having a minute thickness or change in the dimension, so it will affect the results. Okay. Even 0.1 mm or 0.02 mm will also affect the results. So here, to select this resonator 3, now the entire structure is selected. Right click and then edit, duplicate. You can use this edit operations or you can choose this around axis in the top. So again, you are going to duplicate this resonator around z axis 180 and total number as 2 and click OK. Now press Ctrl D and you can able to see this newly created resonator 3_1. Here you can see under the solids. So 3_1 is actually the duplicated one. So double click on this and rename this as resonator 4. So 1, 2, 3, 4. So now you can see all the resonators are created. Now we have to create that input to this structure. So all these top are all conductors, that's the copper material. Okay, and even the ground plane at the bottom is actually a copper material. The thickness as 0.02. So perpendicular to this XY plane, that is the horizontal XY plane, perpendicular to the structure, we are going to create a port at end of this resonator 4 and then the resonator 3. This is actually touching at the end. So we are going to give that input at the end of this one. So for that I'm going to use fit selector and then pan. So zoom in, zoom the area. So you can choose this one and you can draw the rectangle here. So if you want to create a port for these structures, normally for multi-layer design, you have to go for rectangle. Okay. So you can use the lumped port that will touch the top conductor, that is the resonators, and the bottom ground. Okay. So here you can see in the top right, you can see the plane is there. So we are actually in XY plane. So the perpendicular plane is actually the XZ. So here you can see in the bottom right. So this is XZ is actually this plane, perpendicular plane. So go to draw a rectangle and draw a rectangle at this end, this side, and then go towards the bottom. So the rectangle is actually the one is created. So randomly have created a rectangle perpendicular to this one. The rectangle one is actually the port one. This something is greater. So below the rectangle, doubling on create rectangle. So now we need to change the X size. Okay. So Z size is actually -64. From the top 1.62, we are going towards the bottom up to the bottom ground. So it is going -1.64. -3.12 angle. Okay, so it is -3.12. So this width of the port is same as the resonator's width. The resonator 3 width is same as the port width. That is X size. So it is -3.12. Click apply. So the Z size is actually the from the top of the resonator 3 up to the bottom ground plane. That is height of the substrate is 1.6. The top is 0.02. The bottom again is 0.0. So total height is 1.64. Click OK. Now select the port 1, right click, assign excitation. So you have to assign the input at one at the end, assign excitation as, and then lumped port. Okay, so we have to choose the lumped port. So now if you're going for the excitation as lumped port, this should touch two conductors. So here in the case, actually it is the port is touching the top conductor, that is the resonator 3, the bottom ground plane. Choose lump port. You have to use one of them as a reference here. So I am choosing the ground plane as a reference. And so automatically it will highlight in the background. We choose the ground plane as a reference. Okay, so if it is enabled, you can see in the background it is highlighted. So click OK. So similarly, in the opposite direction, you need to create the port. So I can duplicate this port 1 to this opposite side. Okay, so and you can manually assign the excitation, and there is an option called while duplicating we can able to duplicate that excitation also. So I will tell how to do that one. So go to tools, options, okay, and then general options, and here you can see in 3D modeler options, expand, and you can see in the history tree you can see option called last or on Genesis right, and go to HFS option. So go to HFS and then boundary assignment. So enable the option duplicate boundaries and mesh operations with geometry. So while duplicating a port, the meshes on boundaries or excitations, everything will be duplicated along with the geometry. It is already selected. So just I am telling this is the option you need to enable. If it is not enabled, yes, I click OK. Now select this port 1 that is under the lumped port. Here you can see this assigned, and you have to choose this port 1. right click and then edit, duplicate around the axis. So again you have to choose at 180 degree. I'm going to duplicate, so choose Z axis as around 180 degree, total number 2, click OK. So on the left side under the project manager window, you can see expand your attributes design one, expand your excitations. This is the first excitation on this side, and this is the opposite side, this is the excitation 2. So it is duplicated. It is not properly duplicated, so I will right click and then and I will delete and reassign. Okay, so I am selecting the port 2, double click on the port 1_1 and rename this as port 2 and then click OK. Now select the port 2 and then right click, assign excitation lump port and choose the ground plane as reference again and then click OK. Now you have expanded to, now it is coming seeing like the port 1. So previous there is a bug actually there. Okay, so now it is assigned properly. Now go ahead with validation. So what are the options left? So you have to create a analysis setup and then the edition box you have to create. Okay, so we'll draw region. So here you have to choose a region as absolute offset, then the value as dynamo. Okay, and then click OK. Press Control D. The radiation box is created, so you can change adjust the dimensions in each direction using the create region. So here under the region you can see we rename this region as radiation underscore box. If you want to use space between the characters, you have to use underscore symbol. And then transparency you can use some values. We are giving extreme transparency value as 1. Then click OK. So under the radiation box, you need to go to create region. So only for the plus Z daring data. So actually, we are created in XY plane. So we are going to see the fields. Actually, in the top of steps we have kept that filter. That is the radiating structure. So normally the radiations will be moved towards the Z directions. So in that direction, I'm going to keep it as a lambda by 4. In the remaining directions of the radiation box, I'm going to keep that minimum in order to quickly analyze with less meshing. Okay, so that is with 10 mm. So if your antenna is in the omnidirectional antenna or any other structures radiating this similar direction, another any in the directions, if you want to see that and calculate the radiation in that directions also accurately, then you can give lambda by 4 equally in all the directions. For now, I'm going to keep it as only in this direction, the top Z, I'm going to give it as lambda by 4. So click on create region and plus Z padding data, I'm going to keep it as the plus Z padding data means in plus Z directions how much radiation box size. I'm going to keep it as only that 32 mm. So now we have to select the radiation box and we have to apply the boundary. So you have to assign the boundary for this radiation box with boundary as radiation, then click OK. So now under the analysis setup in the left side in the project manager window, so we need to create a simulation setup for which frequency you are going to simulate. So go to advanced and you have to enter the frequency, which frequency you have designed this one. So you have to enter the value. So this 2.4 GHz, 20 passes. So this 2.4 GHz, 20 passes. And maximum delta is 0.02. Click OK. So here I'm giving value from 1 to 4 GHz. Number of points I'm giving as 201. So I'm giving 201 frequency points between these 1 to 4 GHz. Yes, and I'm going to keep it with interpreting sweep types, enable save fields. Click OK. So go to HFSS, save this one first. So either click on save button, or can go to PC. So you can save it in any particular drive. So once I've saved, clear the messages here in the message manager. So go to HFSS and then validation. Everything is fine. Okay, so now go to HFSS analyze all. So analyze all will start the simulation. So you wait for the simulation to complete. After that, we will see the results. So now the simulation has been completed. You can see in the message manager. So including frequency, complete converge, and normal completion of simulation on server. You can go to the results under the project manager, the results. So right click the results. So if you choose a model solution type, you can choose model solution data report. If you are choosing terminal solution type, that is driven terminal, choose the terminal solution data report rectangular plot. So choose the S11 and S12 or S21. Okay, so first one is S11 and S21, and then function as D. So we are getting the results around nearer to 2.4 GHz. Okay. And similarly, you can get the S21. That is near to 0 dB. Okay, so insertion loss is very low. And still you can right click and do marker, add a marker. If you want to measure the points on the frequencies, you can click here. What is this frequency you can measure here? Or you can delete this value. If you right click, go to marker, add X marker or Y marker. So I'm just adding X marker. So click here and move this X markers. Okay, so if you want to measure the bandwidth, you can use it X marker. Again, right click, add a marker, X marker. So two markers are there here. If you want to measure bandwidth, you can use this. And similarly, right click, marker, add Y marker. The Y marker is starting from here. You can drag your mouse and move towards the minus 3 dB. So here is the line. So double click on this one and go to Y marker. And the marker maybe value as minus 3 dB. So automatically the line gets adjusted to the minus 3 dB. So now keep this to the meeting point of this one. So you can adjust the marker and you can find out what is the bandwidth. Okay. So highest frequency minus lowest frequency at meeting point at minus 3 dB scale at that S11. Okay, so here you can see meeting point of 3 axis. Okay, and similarly here. On this point, it is meeting at this side. Okay. So what is the minus 2.73 GHz, and the lowest frequency is 1.92. And this is actually the bandwidth. So that is 0.81 GHz. Similarly, you can export the results. Right click, go to export. Export the CSV file, BFE GIF file. Okay. And go to the HPS design one. Similarly, you can right click the results, go to the source and data report, Smith chart, use S11, report, and click close this one. So here, this is record is actually the frequency sweep curve. So right click, go to marker, add a marker. So for 2.4 GHz, you're just checking. Click at any point on the curve. So you'll get the frequency marked for a particular point with impedance value. So this is a normalized impedance value. So marker point is 2.6 GHz. So double click on this one and enter your frequency. So which frequency is center frequency is 2.4 GHz. So this is around 1.08. That is approximately it's 1. So it is almost nearly matched. Okay. So 1 into 0.8, that is 1.08 into 50, that is around 50 ohm impedance. So it is almost nearly matched. Okay. And if you go to the left side, you can go to the results. So go to demonstration data report, rectangular plot, and then VSWR, and then new report. So x-axis frequency and y-axis VSWR. So go to marker, add a marker. So we can click at any point for this frequency. So 2.4, we have to edit. Value is around 1.28. Okay, filter VSWR. Okay, for 2.4 GHz. So that we want to create terminal report. It will jump to the design. Now click on the radiation box, and you can see here a lot of options are there in the top left. You can see human icon with cross red mark. So click on this icon, so it will hide the radiation box. It will not be deleted, it is hide just. Press Control D. Now go to here in the center, in the planes. So actually, in XZ plane, that is a perpendicular plane. So here you can see the grid line gets in Z. So choose to XY. Now we are going to select all the things. Control A, right click. After selecting Control A, all the objects are selected. So go to plot fields, E. So I'm going to plot the electric field, that is the magnitude of electric field, and then done. Okay, so here this is the fields. So still we can rotate. Here you can see the scales. E field scale is there, right? So maximum field, it will show the maximum electric field intensity levels and all. Double click on the C field scale. Yeah, property window will pop up in the top left. So go to the scale tab. So normally in linear scale, it is very difficult if you want to see field intensity levels clearly. You can go to the log scale. Okay, so from linear to log scale. So from you can also limit the field intensity levels from minimum to maximum. So you can use limits. You can limit the fields. How much fields you want to limit, like 0 to 1000. 1000 volts per meter. So you can limit 2000 or 5000. So for example, I'm going to limit to 3500. So apply, we can see so how much field levels are there in this maximum fields in this area. Okay, so we can contain that also. So now the red color indicates the maximum field levels. Actually, this is the port 1. So here on the left side, excitation 1 is this side. So you can rotate your design. So here you can see the excitation 1 is selected. So that is actually the pixel. So this is the first excitation. Okay, so for the port 1. So normally in HFS, the first port is excited with 1 watt or 1 volt. Okay. So it is a terminal solution type, it is 1 volt. Okay. So here, so from this first port, normally the fields will go towards the resonator, propagate along the resonator, and there will be some gap is there, right? So in between the gap, the field gets coupled from resonator T to the nearby resonator. So again, it will go from this to this. and up to a certain point it will couple with the nearby resonator. So again it will go to the nearby resonator and it will propagate along this. At the end of this port 2 it will reach. At this port 2 it will reach. Okay. So similarly, if you are excited port 2, it is not excited defaultly. I will show you how to excite it manually as a port 2. Okay. So here in the field overlays, first we will animate and we will see the fields. Okay. So select the magnitude of E1 and then right click, animate, and with respect to frames, how much frames for certain degrees we can animate and see. So now you can see this is a point where we are giving input to this one. So here you can see the red color, the maximum fields are propagating, and here you can see there is a gap between the field gets coupled. Just traveling towards this one. When this field is moving towards this area, field is coupled. This is going towards this and is coupled. This is going towards the opposite. So this is a parallel couple line filter. So you can increase the animation speed in the top left, and similarly you can change the excitations from port 2 to 1. The default number is from port 1 excited, from 1 to 2 fields are going. So now right click the excitations, edit sources. So here you can see the first port is magnitude as 1 volt, 0 phase angle, and second port is 0. So second port is not excited. So I am leaving the second port with value as 1 and first port with value 0. So one of the port has to be excited. Both at a time cannot excite. Now click OK. Now you can see the other changing direction of the fields from port 2 to 1. So here you can see fields traveling towards the port 1. From port 2 is moving towards this side, again this side. Then you will reduce the speed of this animation, then you will get a better idea. Okay, so clearly you can see the. So you can export the animation. You can click on export, and you can save the animation as animated zip file or WebM file. There's a video format AV and WebM, and this is the interchange format is animation file. And you can later, for example, I'm saving in desktop, and then save name as one. So I'm saving in D drive. Okay. So it will ask whether you want the animation in black and white, grayscale, how much you want to give, or either it will ask. Okay. And then compression formats and it will ask. Okay, so you can give the compression techniques. Okay, so click OK. And close animation, and you can open that drive, and you can see the file name as one. Open. So we can use that VLC media player, definitely it will open. Okay, so the codec is not supported with the default Microsoft browser, the Microsoft video player. Okay, so you can open with VLC, it will open. Okay. So this is a Microsoft line, that is a couple line filter. So here in the help, in the top, you can see help, SFSS PDFs, and then getting started guides. So there is an example for bandpass filter. So this is a bandpass filter using a coaxial feeding. Okay, so and that's like a cavity based bandpass filter. So a box's cavity is created. You can see the cavity. In the center of the cavity, I actually created different resonators. Okay, and then you are using a coaxial feeding technique. So this is also available. This tutorial is available inside this software defaultly. So I want to tell you one thing. Like there is a student version available for all the people. Okay, so anybody can go to the ANSYS website. Okay, you can search for ANSYS electronic student version, and you can download the software freely from the portal. So there itself they have given what are the software requirements and hardware requirements. So it will be minimum 4 GB RAM required for the software. Okay, and there will be some limitations like you cannot able to simulate a larger structures. Okay, so that is a free software. Okay, so you can use it. Actually, it was released before 1 month. Okay, so HBuzzers, you can go to that. You can download from that ANSYS website. So here this. So from that student version also, the lot of tutorials same like that it will be available. Okay, so you can practice this same filter also whenever you want. Okay, so up to the field results, everything they have shown. Okay, so you can see the filters as parameters for that one. The step-by-step procedure with all the guidance is given in that material. Okay, so how to view the fields. So you can check that tutorial. And even certain examples is there. So we go to file, open examples. So under HFSS and the RF and microwave. So here that same design is created is there. So you can see a lot of examples are there for RF and microwave and arts antennas. So I'm just opening the example. So this is that example I have shown tutorial, right? So this example is available in file open. You can go to HFSS validation and you can simulate and you can see the results. HFSS analyzer and you can see the results. Okay, so all the examples are available. So uncheck the plot visibility, the field results will appear. So once a simulator, you can click on save button to save the simulator results. Okay, and then you can close. So if you have any doubts related to the filter session, you can ask me now. The substrate is actually FR4 substrate. Okay, it is a normal standard substrate I have taken. So if you have any questions, you can ask me now related to this filter design, or you can close this one. Can we simulate antenna fractal? Oh, in HBuzzers we can simulate the antenna fractal. So any other questions?
The floor is now open to questions. Please unmute and ask questions.
Solver is defaultly FEM. Okay, actually, HFSS default is FEM. For this design, is actually we have used FEM.
If we have no other questions, then shall we wind up the session?
Yes.
Okay, thank you, Karthikeyan sir, for delivering the very informative talk. And on behalf of the
Thank you, ma'am.
institution and the participants, I express you our sincere gratitude, sir.
Thank you, ma'am.
And thank you, participants, for your active participation in the session. And so we can wind up for tomorrow. For today, thank you.